Assalamualaikum. So this is part 4 video for natural convection heat transfer. Combine natural and forced convection. When a surface is subjected to external flow, the problem involves both natural and forced convection. Heat transfer coefficient in forced convection are typically much higher than in natural convection. The error involved in ignoring natural convection may be considerably at low velocities. Nusselt number, forced convection, flat plate laminar flow. Nusselt number for forced convection is directly proportional to the Reynolds number with the power of 1/2. Natural convection, vertical plate laminar flow. The Nusselt number for natural convection is directly proportional to the Reynolds number with the power 1/4. Therefore, the parameter of ratio Grashof number to the Reynolds number power of 2 represent the importance of natural convection relative to forced convections. Combine natural and forced convection. The relative importance of each mode of heat transfer is determined by the value of the coefficient Grashof number divided by Reynolds number power of 2. Okay, I already explained in the first video of this relation, but this is the further detail of the explanation. Natural convection effects are negligible if the ratio of Grashof number to the Reynolds number power of 2 is extremely small than 1. Free convection dominates and the forced convection effects are negligible if Grashof number divided by Reynolds number power of 2 is extremely large compared to 1. Both effects are significant and must be considered if the Grashof number by the Reynolds number power of 2 is approximately equal to 1. So for this case, we need to consider both the natural convection and also the forced convection. Natural convection may have a hurt forced convection heat transfer depending on the relative direction of buoyancy-induced and the forced convection motion. As you can see, we have three figures, two with the blue dotted line rectangular, which suggests it helped the forced convection, and the last one hurt the first forced convection. Okay, the first one is the assisting flow, which the induced flow or the forced flow is with the same direction of the natural current convection. So this kind of thing, the buoyancy motion is in the same motion direction as the forced motion. So the natural convection assists forced convection and enhance the heat transfer. And for the case of on your right hand side, where the force flow is opposing direction to the natural current flow of the natural convection, so it is called the opposing flow. So the buoyancy motion is in the opposite direction to the force motion. Natural convection resists force convection and decrease heat transfer. And last case for the figure in the middle, so this is the transverse flow, where the buoyancy flow is upwards and the force flow is from side. So buoyancy motion is perpendicular to the force motion. So the transverse flow enhance fluid mixing and thus enhance the heat transfer. So this three is the example of the natural convection and also forced convections. Nusselt number for combined natural and forced convection, mixed convection. A review of experimental data suggests a Nusselt number correlation of the form Nusselt number combined equal to Nusselt number of forced convection with the power of n plus minus Nusselt number natural convection with the power of n, and all of it with the power of 1/n. Here the plus and minus sign is referring to the assisting flow or opposing flow. Whether the plus sign is for the that help the forced convection, and the minus sign is for the one that is hurt the forced convections. And here n is in the range of 3 to 4, but Normally we use 3 because the value is approximately accurate. So Nusselt number for force and Nusselt number for natural convection are determined from the correlation for pure force and pure natural convection respectively. So combine natural convection and radiation. Gases are nearly transparent to radiation, and thus heat transfer through a gas layer is by simultaneous convection or conduction and radiation. Radiation is usually disregarded in forced convection problems, but it must be considered in natural convection problems that involve a gas. This is especially the case for surfaces with high emissivities, which we can calculate the heat transfer rate. Total heat transfer rate is equal to heat transfer from the convection plus the heat transfer from the radiation. The radiation heat transfer from a surface at temperature Ts, which is the surface temperature, surrounded by surfaces at the temperature of T surrounding, is radiation. Heat transfer from radiation is equal to sigma times epsilon times surface area times the power of 4 of surface temperature minus the surrounding temperature. Sigma here we use the Stephen Boltzmann constant, and the radiation heat transfer between two large parallel plates is calculated by this equation, which I put in the pink color, and epsilon here is the effectiveness of it. So there is a note here: when T infinite or surrounding is smaller than surface, or and the surrounding is larger than surface, convection and radiation heat transfer are in opposite direction and subtracted for each other. So for these cases, which I put in this note down here, the total heat transfer rate for convection and radiation will be convection minus radiation, or the other way around. Okay, this is the end for part 4 of natural convection. Thank you.